Right, good evening, everybody.
Yeah.
Thanks for joining. This tonight's seminar is one we held over from 2 or 3 months ago. So it would have been Phil Hilton West who would have been introducing it. My name's Steve Arnold. I'm the new CIBSE North East chairman. And we've got tonight Gerard Hosford from DESCO, who's going to present on the Viking Energy Network in Jarrow, which is a heat from river water scheme that DESCO are carrying out. So without further ado, I'll let Gerard from DESCO take the floor.
Thank you very much. Can everyone see my screen okay? I hope so. Good evening, everyone. I'm Gerard Hosford from DESCO. I'm Technical Director. And tonight I'm going to be talking about the Viking Energy Network. So this is a new district heating network that South Tyneside Council is in the process of constructing just on the banks of the River Tyne in the northeast. I'm not sure if everyone here is from the northeast or we got people from further afield. So it's a new build energy centre. It's going to provide heat and a private wire network from the energy centre to primarily council-owned buildings in Jarrow. So the idea of it is to give a low cost, low carbon heat solution to the council. I think the council's main driver is the carbon agenda. Obviously, it's on everyone's radar at the moment. So this presentation I'm going to do is going to cover a project overview, key drivers, the technologies involved in the actual network itself, any kind of project challenges and lessons learned that we've had during the design so far and construction. So as I was saying, in terms of the project overview, it's a new build private district heating network and a private wire network. It's known as the Viking Energy Network in Jarrow. The acronym is VENJ. So it's designed to serve a number of buildings with allowance for future expansion in the future if the council want to add on to the network, or if there's additional buildings built in the area could potentially be connected. The main driver in the piece of technology in the energy centre is a river source heat pump. So basically that takes water from the River Tyne and basically passes it through the heat pump. It's an ammonia heat pump and it generates heat. Obviously uses some electricity as well, but that bit of technology does the base load for the network. We also have a PV farm and we have a battery energy storage system on site as well. The scheme has got some ERDF funding, which has assisted the council develop the scheme. It's a sequel accredited scheme as well, which is good, and obviously there's all the criterion credits that go with that. DESCO are appointed as principal designer and a lead designer basically in April 2019. So we've been working on the scheme for a few years now. The scheme started on site in March of last year and is due for completion spring 2023. The main contractor on the project is a specialist district heating contractor called Kilowatt. So in terms of the key drivers for South Tyneside Council for the scheme, it's obviously every council's desire at the moment to reduce carbon. The carbon footprint, energy costs for the council as well. Obviously try and minimise energy costs to deliver an affordable scheme to building users and residents. I think the development of heat networks or district heating in the UK is increasingly recognised as an important component in the UK's future strategy, and I think that's kind of leading and helping a lot of local authorities have their own district heating networks. As well as that, the other driver is to improve the security of energy supply by diversifying the energy sources and heating and reducing dependence on fossil fuels and imports, etc. The last one is to offer supply of heat that's good value and contributes to reducing fuel poverty as well. So they're the kind of main drivers for the South Tyneside and wider development of the scheme. In terms of who's involved and the project team there, obviously the main, our client is South Tyneside Council. We are, as DESCO, are the lead MEP consultant and principal designer, and we've got some sub-consultants working underneath us. That includes the civil and structural engineer, border design, the architect base. We've also employed a HV designer as well to do some of the HV stuff, like IUS to do that. And Pal Frischman is the CDM advisor. They're part of the DESCO in the DESCO group of companies. So they're sitting alongside us doing that CDM role. And on the client team, which is appointed direct, we've got the planning consultant, Cogio, the SQL assessor, Wood, Royal Haskoning, who are the marine engineer, and Thornton Firkin are the QS, and they're also assisting with the project management for the council as well, the overall project management of the scheme. In terms of the project plan of works, DESCO duties, we're a principal lead designer. We had to do the feasibility, upfront feasibility for the scheme as well, and that included Techno-Economic modelling. We've done the design to Rebus stage 4A. There is some contractor design elements on the scheme as well, and we're client side working with South Tyneside Council at the moment. So we're currently at pretty much stage 5 as we stand. And in terms of the stages of typical stages of district heating network, this what you can see on the right there is from CP1, Code of Practice for District Heating, and it just shows in terms of the stages of a typical design and construction operation of a heat network where we're at the moment. So we're currently in construction of the network as it stands at the moment. Network overview. So basically we've got a number of different types of buildings connected to the district heat network in Jarrow. I won't go through every single one of these, but basically they're a mixture of schools, offices, Jarrow town halls on there. We've got a Parmas hospital, which is more of a kind of a daycare hospital at the moment. We've got like an activity centre, that kind of thing. So it's primarily offices, resi in terms of tower blocks, and some healthcare there as well. So that's the district heating network side of things. Not every building is going to be connected straight away to the network. So the names of the buildings there you can see in bold are the buildings that are going to be shown connected initially to the network, and obviously in the future we'll be connecting those other buildings. In terms of the private wire network, we're connected to the Energy Centre building itself, so obviously the Jarrow Town Hall, the Fab Club, I should say club instead of clun, and the tower blocks as well. It's primarily the plant rooms for those. And also for the town hall, we've allowance in the network for adding EV chargers at the town hall as well. So the private wire network will feed those as well. But just to get kind of a feel for where we're looking at, this is just like a Google Images overview of the area the network covers. So you can see over here, this is where the energy centre is. Obviously this isn't the scale of the energy centre itself, it just gives a representation of where it's actually located. Obviously you've got the River Tyne there, and basically we're running the district heating and private wire network along down here. It's about 4 kilometres of network, maybe a bit more actually. It just gives a feel for the different buildings that we're connected to across the network. We also have some stub connections here as well, and here for future network expansion. So the actual energy centre site location itself is here. The energy centre building is basically going to sit, I'll come on to it anyway, I've got some more detailed drawings, but energy centre itself sits here. We've got the PV array, and then we've got the river and the water abstraction here. And you can this just gives a feel for the where the energy centre is, and there's some challenges associated with this kind of site as well, and its location by the river, which I'll come on to later in terms of lessons learned and stuff. So the existing buildings that we're connecting to, they're all existing buildings with a mixture of different types of technologies for space heating. Pretty much all of them are gas-fired buildings with central plant rooms, and there's some buildings with some electric storage and radium or etc. So primarily it's gas-fired heating where that those buildings are using. I think this spreadsheet was done early feasibility. So what we did is we went around to each building, did a survey of each building, the plant room, what plant was in there at the moment. We did the survey with the aim to kind of understand whether we could actually connect the district heating network there onto that building. What are the pros, cons, strengths, weaknesses of doing that? Obviously, with a central plant room, it makes it a bit easier because you can just connect the district heating network in that plant room, and you don't really have to do any you have to do limited secondary side modifications. So most of the buildings that were selected for connection did just that. Another key considerations, understanding what the existing temperature operation is for the connected buildings in terms of delta T's, etc. Because obviously, if we're connecting to old buildings, that can have an impact on the overall efficiency of the network. So we have to really understand that in order to do some of our techno-economic modelling and financials and all the rest of it, and carbon savings. And obviously picking the right technology as well. It's key to get the size right of the technology back in the energy centre. So in terms of the energy centre Riverside site, as we call it, the MEC systems on the site are obviously incoming gas and water. We've got one number water source heat pump. The manufacturer is Star, based in Glasgow. It's a 700 kilowatt thermal unit, just slightly under 696 to be exact. It's got a COP of 3.25, although that does vary across the season. We've got in the energy centre space for an additional heat pump as well to be installed in the future for either a change of technology. Obviously with gas obviously under scrutiny at the moment, we could obviously maybe put another heat pump in, or if the scheme extends, we can put that heat pump in as well. So there's some flexibility in the energy centre itself to put in an extra heat pump. We've got we're putting in one gas-fired CHP. It's just quite a small unit, 63 kilowatt thermal. Initially we did have a larger unit, but we scaled that back quite considerably to try and just run it as flat out as possible. But the plan is to have the heat pump doing the base load and the CHP kind of helping with the shoulder periods, and we've got gas boilers in there as well to do that the peak periods in winter. So we've got two gas boilers, 788 kilowatt output per boiler, two thermal stores, each 50,000 litres capacity. We've also got all the flue and ammonia venting and the chimneys from the ammonia system, the BMS system, and all the rest of it, all the pipework, etc., that goes with an energy centre. The current operation, the initial operation of the energy centre's pipework in terms of flow and return temperatures is 75-55 degrees C, but we're aiming to kind of reduce that as the scheme develops. When the scheme's live, the council are potentially going to do some secondary side building modifications to try and lower that return temperature. But it's quite difficult to do that theoretically. A lot of that can be done. It can be estimated theoretically, but you really need to have the scheme running and do some of your tweaks to try and optimize the network. So that's the aim, and that'll improve COPs, etc. as well. So in terms of the district heating network, for those of you that aren't familiar with a district heating network, this just basically gives an overview of what it entails. So you've got your energy centre, which has all your boilers and whatever kind of technology you have for your heating. You've got the heat network, the connected buildings, and the building end of use systems. So you like your radiators, your hot water systems, etc. In terms of what we did for the network, it consists, in terms of design, it consisted of the below ground LTHW district heating pre-insulated pipework. So that basically is installed below primarily soft dig areas where we can do that. But obviously, because where we are in the world, there was obviously some hard digging. We're under roads as well, so obviously there was a lot of coordination to do with that in terms of highways, ownership boundaries, all that kind of stuff. So a lot of work went into the actual routing of the network. The installation of the below ground LTHW pipework, and it took a lot of civils investigations and desktop studies, and also GRP studies. Now we didn't do all that. That was done by a lot of that was done by the contractor, but we got a lot of the kind of desktop information to allow the contractor to kind of have as much as possible before they went and started on site. There was a lot of approvals associated with the district heating network as well, and pipework installation. Building more connections to and from the connected buildings. You know, it was with a network like this, it's all well and good having drawings and our designs, but a lot of it's down to, you know, the feasibility of connecting. There's lots of obstacles in the way, you know, below ground or ownership that we have to consider. So that was a big part of the design as well. Interface with building plant rooms, including plate heat exchangers, thermal stores, etc. Getting that agreed with the end users was quite important as well. So we did a lot of that up front as well before we really started in the detail design. In terms of the electrical systems on the site, on the energy centre site, we have obviously the incoming DNO network. Yeah, incoming DNO, which is Northern Power Grid. We have the HV and LV switchgear and transformers in the energy centre as well. The PV array was just under 8,000 metres squared of PV array with 1 megawatt output. Again, that's basically all installed on the ground at the energy centre site. The containment and wiring associated with the energy centre, that's all in there as well. We have the battery storage system, light and small power data. So all that kind of stuff went into the energy centre actual building itself. So like the connection to the local HV network from the current distribution operator, that will assist in the event of any kind of abnormal short-term peak loads, essentially. So that the PV will will basically feed the private wire network, and any kind of, when we don't have enough power, that will be imported from the grid. So the network itself, the VENJ private wire network, will generate and supply electricity over the dedicated HV cable, and that will go to a local substation and feed the buildings that we just talked about at the start of the meeting there. So the battery that we put on there is a lithium-ion battery. Has a round trip efficiency of 90%, battery life of 10 years minimum, and the battery depth of discharge and maximum 80%, I think, from memory on that one. So I think the use of batteries is becoming more common, I think, in building designs and energy centre designs as well. And putting the battery on there will, and the kind of main aim to do that is for the proposed operational strategy. So it'll utilise the generation of the batteries. Utilising the batteries will mean that the water source heat pumps, obviously the water source heat pump runs on electricity as well. So by storing some energy on site, we can make sure that we can run the water source heat pump and have it operating on a carbon neutral basis for much of the summer periods for domestic hot water generation as well for the connected buildings. So that's one of the aims for doing that. That hadn't had a big impact on the financials as well. In terms of the private wire network itself, the route of the private wire network follows the same routes as district heating. So in terms of keeping costs down from civils and excavation, you know, that it's all within the same trench. Obviously, the spacings as per NJOG and streetwise requirements. There's also comms ducts as well that run the length of the network for communication between the actual buildings connected and back to the energy centre and its metering and controls, etc. We've got one new 500 kVA package network substation that's located just outside Jarrow, near Jarrow Town Hall. Again, along with the district heating pipework, it involved a lot of coordination, planning, building control, approvals, all that kind of stuff. And the usual builders work connections and below ground coordination was also there's a lot of work associated with that. In terms of the network, I'll just talk a bit about the thermal profiles and the techno-economic modelling briefly. So the techno-economic modelling, which we did, was done upfront at feasibility. So we had to obviously estimate the loads required for the network, and that was the thermal loads and electrical loads. And we had to do an appraisal against a business as usual type scheme of existing gas boilers in the in each building. A lot of these buildings as well, some of the buildings are old, and the plant in some is old as well, so we had to consider the costs of replacing them versus the costs of connecting a new district heating network. So we did all that up front as well. And just in summary there, that the technical modelling includes network energy profile modelling, plant size and optimization, which is key as well, because it's very easy to oversize some of these networks. So we had to make sure that all the diversities and all that were as per CP1. Network financial modelling, running costs and payback, and network carbon savings and modellings as well were done. So in terms of the actual predicted total load profile, so the maximum load of the network is just under 4 megawatts. The base load is about 700, and that's why we've selected the water source heat pump to be sized on that base load. So that will run primarily all year and be topped up by the CHP and boilers at the shoulder and peak winter periods as well. So the aim is to maximise the heat pump operation. So essentially, that gives you a flavour for kind of loads we're looking at. In terms of the proposed plant mix, obviously you can see there that the heat pump does primarily most of the loads, and it's topped up by the CHP. But you can see that even though we've got the gas boilers in there, they're not really running as flat out as the water source heat pump. So all the technology mix is based around this strategy as well. In terms of the PV, so in terms of PV generation, we did our solar modelling to just generate, estimate how much PV we would need to generate the output that the council was wanting. So you can see here, shows you the output we're getting from the PV, which is over just a megawatt here. That profile was done as well. In terms of the predicted financials and carbon savings, you can see that, just a caveat on this, these are based on 2019 figures that we did at the time. So we're saving just about £100,000 roughly a year. This doesn't include the RHI benefits, so that kind of gives you a flavour for the savings per year associated with the business, compared with the business as usual case. And the carbon savings as well, you can see there. Obviously, there's tons of carbon saved by utilising this network for the council. Riverside Energy Centre site. There was quite a lot of externals associated with the site in terms of civils. Again, we're not civils. DESCO aren't civil consultants, but we appointed Border Design to do the civil and structural design for the scheme. The nature of the scheme, obviously, in the site meant that the ground conditions were quite poor. There was a lot of development and different types of historic development on the riverside where we're putting the energy centre. So the ground conditions needed to be considered up front, and we had to do some design modifications to the actual structure. So that's actually a pile structure for the energy centre in areas as well to deal with some of the poor ground conditions. So that was quite a lot of design went into that. In terms of the civils itself associated with the energy centre and the riverside site, we had the below ground drainage, the water extraction. Initially we had a bridge, initially we had a pontoon, but this was changed to a bridge and platform. Riverside and associated structure and civils works, all the pumps and filtration which are located on the bridge, the water source heat pump, infiltration system, which again was pontoon mounted, but is actually bridge mounted, which I'll come on to later. And a new access roadway from the main carriageway as well. Obviously, we needed to put a road into the site to access the energy centre. All the CCTV and security systems as well associated with the externals. Obviously, that was a DESCO element. We didn't actually do any demolitions to the Staithes in the end, but it was looked at initially. But we actually managed to keep the Staithes in their current form and utilise them for the abstraction, which I'll come on to later. So in terms of the actual site itself, now this hasn't come out great on the actual presentation, but this is a drawing of the energy centre Riverside site. So you've got the new build energy centre here. You've got the PV farm here. This is the road, the new roadway. This is the main road, and this is the new access roadway to the energy centre and the PV farm. Over here, we've got the abstraction bridge. So on the actual bridge, we've got the abstraction pumps that basically extract the water from the river and basically pump it via underground pipework all the way back to the energy centre. That goes through the heat pump and then it goes back out into the river. We've got a dedicated below ground pipework system here that basically discharges the river water back into the river. So there's no chemical change of the water or anything. It just basically comes out, it's filtered via rotary filters on the bridge and basically runs back to the energy centre. We're taking some of the heat out of the water and putting it back into the river again. In terms of the design development, obviously very early days, because obviously we were the lead consultants. We had to design basically an energy centre. The energy centre building itself is a functional building. It's not one of great architectural merit. It's to primarily house the actual plant and do a job. So how we started is we just basically did some spacing analysis of what we needed in terms of, heat pumps, plant boilers, switch rooms for the private wire network, everything that needed to fit into that energy centre. We needed to kind of just plan that out, and basically we just developed that with the architect into a final kind of drawing. Again, I had to go through planning, etc. As well, I was talking about the river water abstraction. That was one of the main challenges of the scheme, is to get a solution that actually is buildable and how we get the water out of the river without, disrupting any ecology. There's mud flats in the area as well, so we have to consider all that kind of stuff, land ownership boundaries, all that. So there was a lot of upfront design done to try and come up with a solution to get the water out of the river. We obviously had the Staithes there as well. So initially when we started looking at this, I did reference pontoon a few times. Now the actual scheme where it actually built doesn't actually have a pontoon, it's a bridge. We did that because at the time when I went out to tender, the pontoon we knew it was a buildable solution and it wasn't relying on the structural integrity of the existing Staithes. But when we had the contractor on board, we kind of worked through that further, and it was decided to put an actual bridge on rather than a floating pontoon for river water abstraction. So essentially, we worked through some of the concepts with the manufacturer. This is a generic heat pump that we're looking at. This is just taken from our front feasibility study. It's not the actual VENJ heat pump, but I'll come on to that later. I've got actual photos of that one that's going to be installed. So essentially, what we've got is the river water. Where we've got our abstraction pumps, and they sit just below the water line. They extract the water up. There's also rotary flush filters as well that basically gets all the sediment and stuff out of the water, and that's passed through. The filters are actually before the pumps. So basically, it's filtered, rotary filters, then the pumps. Basically, we're run from the bridge to the energy centre. And that goes through the heat pump, as I was saying earlier, and back out into the river. There is space and connections on the design for some future silt, future enhanced filtering as well, because in some of these locations, mussels, etc., can migrate into the area. Now, at the moment, there isn't really any mussels came up from the studies that were done. But if mussels and larvae start forming on the heat pump, then it can just degrade the heat pump and essentially require replacement. So we've put in some, if there's any changes in ecology in the future, there is space to put in some additional filtration as well. So in terms of the energy centre building, these are just some concept images for planning. You can see it's essentially a shed, a large port frame shed building to house the actual plant itself. So it's just a functional building really. Again, that kept costs down, and it allowed us to focus on the actual technology, spend the money on the actual district heating technology rather than the building itself. But again, it's still a decent building. It does what it needs to do, and it's functional, as I said. This is just like a screen grab. Again, this doesn't come out great on the presentation, but this just gives a flavour for schematically and the mechanical side of things what we've got. So we've got our water source heat pumps here with space for future one. We've got all our filtration here that basically goes into your flow and return headers. That's supplemented by CHP as well when we need it, and the boilers. We've got our thermal stores, and obviously our primary district heating pumps here and all their filtration, degassing, etc. So essentially it's not very complicated, but it's just integrating all these technologies and etc. That's key, and temperature profiles and getting their temperatures and flow regimes correct is key. So obviously that was done by Desco. In terms of the structural design for the scheme, which was done by Border, you can see this is the structural solution for the energy centre building itself. And the water source heat pumps are on the location here. So you've basically got the actual water source heat pump we're installing now is going to go here, and the future heat pump is going to go here. And you can see the structural base. I think each heat pump is 12, 13 tons, something like that. So it's quite a heavy bit of kit. So we need dedicated a slab in order to mount it. And that slab runs to the edge of the building as well. So basically there's an external plinth. So in the future, and for the current install, the heat pump can basically be craned on, because it comes as one package craned on and slid into the energy centre. So all that kind of coordination had to be done up front as well, just to make sure it was buildable with a contractor. And again, you can see all the slabs for this is for the thermal stores, boilers, and pressurization, etc. So that was all built in. And this side is the electrical part of the substation. So we've got a private wire associated plant here. We've got our main incomer here, HV switch room, LV switch room as well. So again, all the trenching's already designed in for that. So obviously the ground conditions, as I was saying earlier, were quite challenging. So there's some gas in the ground, so we had to have a membrane under the slab, and because of the ground conditions, it's actually a piled structure as well to deal with the ground conditions. So again, quite a lot of design went into the substructure. In terms of the actual energy centre itself, these are more detailed drawings showing what we've got in the energy centre. Obviously the heat pump, which is installed here. Now the heat pump, because it's ammonia heat pump, it's got some further challenges. It uses ammonia, so if there's a leak in the ammonia, then the ammonia has to be vented. So the venting actually there's a vent line that runs from the enclosure, heat pump enclosure, up to the chimney. So if there's an emergency discharge, it'll dissipate up here. Acoustically as well, the water source heat pump is actually quite loud. So to save some costs and avoid acoustically, a heavy acoustic treatment of the actual building itself, we asked the manufacturer to build an acoustic frame, a box basically around the heat pump. But again, due to the ammonia side of things, all that had to be ventilated as well. So we had to have just background ventilation, make sure this is negatively pressurized in case there's an ammonia leak. And again, we've got the space here for the additional heat pump. We've got our 2 boilers, space for additional boiler, CHP here, thermal stores, electrical elements of the substation or the energy centre over here as well. So that gives you a feel for what's actually going in there. The heat pump itself, these are just some of the star drawings for the heat pump showing the typical configuration of the heat pump itself. Again, it's built off-site. It's the unit's actually manufactured. Here, these are actually pictures of the VENJ heat pump. It's in Glasgow waiting for road transport to the site, and it will come in one skid that will be dropped outside the energy centre and rolled in, and the all the acoustic and ventilation systems will be done on site, and all the integration will be done on site. So it just gives you a flavour for how it actually looks. In terms of progress, these photos are a few weeks old, and there is some further progress on site. So you can see that the energy centre frame is starting to go up, the chimneys in, all the trenching externals are starting to go in. I think there's cladding now on the building, so it gives you a flavour for what's happening on site. The river water abstraction again was quite a bit of design development on here. So this is kind of how we started out. This is what I was talking about the pontoon. So initially working with Royal Haskonie, because of the risk associated with trying to utilise this existing staithes, it was decided to go to tender initially on the pontoon. So we had to work with Royal Haskonie and the pump manufacturers to come up with like a pontoon solution for the scheme. Essentially, all your pumps are on the pontoon, and your controls are on the pontoon. That's floating up and down with the tides. Obviously, it's tidal, so we have to have some support structure, mooring piles there. So all that design was kind of done for tender. And obviously that pipework runs from the pontoon back to the actual bank of the river, back to the energy centre. These are just some concept sketches to show where we kind of started out. And where we ended up is obviously when we got the contractor on board, obviously there was some value engineering done, and it was decided that a bridge structure would actually be better to do than the pontoon. I think the main cost was associated with trying to pile in the river and make sure that we had actual, because if you think about a pontoon needs quite a lot of support to avoid it floating away or being washed away by the current. So the civils and structure was quite expensive when we started looking into it in detail with the contractor. So it was actually decided to put a bridge, use a bridge instead of the pontoon. So you can see a picture here on the left is the existing staithes. This is just an on-site photo I took a few weeks ago. So that's the existing staithes. This is the footprint for the base basically for that bridge, and that's already been installed. And the district heating, sorry, the pipework from from what will eventually be the bridge is starting to be installed there. But again, you can see the cross section here. You've got your footing here for your bridge, which is there. Got the bridge which will run out, and it'll actually use the staithes as a structure to be able to support that bridge. And you'll have your water abstraction pumps here and your filtration here and all your pipework. So fully accessible, have lighting on it, all the rest of it. We had to do some load testing on this structure as well. So Royal Haskonie, the marine engineer, had to do a lot of calculations and actual live load testing to make sure that the staithes was up to the job to be able to house this bridge. But that's something that we could never really have done without kind of contractor engagement. So hence why it was modified when the contractor was on board. Network route I've already kind of discussed on the previous images, so there's no really point dwelling on that. Again, you can see I'll briefly discuss it because obviously this drone's a bit better than the previous one. So the energy centre itself here, obviously this is the route of the network, basically through Jarrow. This is like the main street of Jarrow here, Range Road as well here. So the actual route planning, that was quite a challenge as well, because we had to liaise with the Highways Authority, South Tyneside Council, and make sure that we weren't stepping on anyone's toes by putting a district heating pipework in the area. Again, cost and efficiency of the routing was all part of the kind of design development as well. This is some photos of the district heating network being installed. Again, a few weeks old, but you can see the district heating network being put in primarily on down the highways. Obviously, still using soft dig where we can, but obviously, some areas we have to go under the highway. I think key challenges, having the site beside the river. It's not something you come across very often, having a water abstraction heat pump system on a river. So again, there was lots of lessons learned there. The abstraction solution, the buildability, river ecology and bathymetric studies, again, understanding the type of water depth we had. Because obviously, if you think about it, if you have extraction pumps in a river, you don't want to be extracting silts like a hoover. So we need to make sure that we had enough water depth at all times to avoid any sediment being sucked into the system. We had to make sure that the bridge was out far enough to make sure we had about 2 meters clear of water at all times. Present cities and stays and how we utilize, again, that was a lot of meetings associated with that one up front. Specialist technology and manufacturer interfaces as well. Obviously, we've got the quite specialist water source heat pump, and getting that right and the interface between our design, their design, and the contractor's design as well was a lot. We'd have to be very careful there, and I think we're at a point now on the design where we are where we need to be, and obviously it's being constructed at the moment. So that was a big lessons learned there. Utilities liaison, which is sometimes a challenge, especially associated with this network as well. Connecting of network to old buildings and systems, which is quite a common common challenge for district heating networks. I think it's all well and good if you have a new buildings that you're connecting to and you can minimize your flow and return temperatures, but obviously you need to make sure that by connecting to this network, it won't impact the operation of the existing buildings you're connecting to. But I think on the other district heating networks that we've done, I think this particular point here is it's like an ongoing challenge, because you can always modify and improve and change some of your parameters to optimize the network. I think that's key. And again, that's a source that's linked with the flow and return temperatures and COP performance as well. So that's the end of the presentation. If you've got any questions, you can ask them now. I think is there any questions on the chat? I can't actually see the chat at the moment.
Can you see the chat, Gerard, or not?
No, I can't.
Oh, right, okay, I've got it. I'll put the first one on. Basically, have you got any idea how the sort of kilowatt hour cost for heat to the end user is going to compare to that's currently available via the more conventional route on the open market today?
Yeah, so it's a good question, that, because obviously when we first did the Techno-Economic modeling was back in 2019. There has obviously been quite a change in the last few years,
yeah.
kind of energy costs and stuff like that. So, like primarily the buildings are connected to are actually council, South Tyneside Council buildings. So I think the aim for the council is always to ensure that the costs that anyone's paying is less than the kind of market rate. And there's still some talks going on. I can't exactly answer the question because there is some discussions going on in the background. The council's kind of setting up a mini ESCO, I think, to look at this kind of thing. So it is a bit of a moving target. So yeah, but it is more attractive than
going conventional
electricity.
Route,
yeah, exactly.
Yeah. There's one from Martin Hewitson here. Water is the permissible discharge temperature of the river source heat pump return to the river. I think it means what is the permissible temperature for the return to the river?
Yeah, we have to, because we're extracting from the river, we have to get a marine license. So basically we have to have an extraction permit essentially. So there was we had to do that was done by Royal Asconi. So we've got a license for that. So there was lots of questions asked from about water temperatures, you know, any changes to the chemistry of the water. So I think we're putting the water river, basically it varies over the year, essentially. So the river water itself can be between 12 and 15 degrees over the year. It can drop down to potentially 10, I think, from memory. So it's only about 4-degree delta T change in the return. So it does depend on the time of year, but it's about 4 degrees.
Yeah.
Drop.
Yeah. The second part of his question: how do the economics stack up without the RHI, and with current energy tariffs? I don't know whether you actually have those figures, but
no, I don't. That's again the RHI.
Probably something Mawson could maybe have answered if he'd been on the call.
Sure, Mawson's on, but anyway, in terms of,
no, I don't think he is actually.
Yeah, in terms of.
Can you hear me?
Yes, Mawson. Yes.
Sorry, just trying to find my mic there. Mawson Kohani, just South Tyneside Council. I think at the outset, before ESCO got involved, when we were looking at the modeling, RHI was always a nice to have, but the economics stacked up at the time without the RHI. And as Jarrow said, recent rises in energy tariffs, that's meant that it's actually a lot more economically viable than we thought it would have been. So I think we're still hoping to achieve RHI, and that would be an additional benefit to us, but the whole thing would have worked without it, if that answers the question.
Yeah. Somebody's asking if they have a copy of the slide deck. We would normally put it onto the CIBSE Northeast website, providing that Gerard or his company would allow that. So
Yeah,
I guess
yeah.
So yeah, in the fullness of time, it might not be immediately, but normally within a couple of weeks, whoever does our web stuff will download a copy onto the CIBSE Northeast website. Jess is asking, hi Gerard, will the battery be used to generate maximum financial return by buying low cost electricity from the grid and possibly sell some back at peak times if there is a spare?
Yeah, that's part of the intent. Yeah, in terms of the design. Yeah. But I think that the main thing is to try and have the water source heat pump operating, as I was saying earlier, on a kind of carbon neutral almost basis as well, to try and store some of the energy from the PV. But yeah, that is built in the design. So we got an export agreement as well on the site, and we can sell back to the grid. Yeah.
Another one, I presume the district heating network will feed BPHA at each connection, and what pressure will be the network operating at?
It's about 12 bar.
Right. Okay.
Yeah.
What do the delivery temperatures look like at a building level? Are they directly connected of individual heat exchangers?
Yeah, so we've got individual heat exchangers in each building. In the hospital, which is still under debate, to be honest, where we're still doing some modelling and some surveys for that. It looks like we're going to have some thermal stores as well, small thermal stores. So it's a bit different for each building, but primarily it's plate heat exchangers. Yeah, Danfoss plate heat exchangers.
Yeah.
Exactly.
The one from Jess, how essential is the 63 kilowatt thermal CHP to the scheme? In reality, will this not reduce the heat output of the water source heat pump over the full year? And there seems to be plenty of gas backup without the CHP.
Yeah, so the CHP is to generate some additional power as well. We did actually, as I was saying earlier, have a larger CHP unit, but we did modelling. That was the unit that we thought we could. That was the smallest unit that we thought would work. It's a valid
essentially the electricity output from the CHP runs the water source heat pump when there isn't any PV or.
Yeah, well, it feeds into it. It's not, you know, that we're going to be importing as well, and using the battery storage, but it does feed into the mix of electrically producing technologies. Can't even talk now.
Yeah. One from Dave Fittis. At what voltage is the private wire network being distributed?
I'm not electoral, so I'd have to do. I'll have
He's
to
actually
double-check
answered it where he sort of suggested
11.
an answer of 11 kV, but
that. Yeah, I think
yeah.
it's 11 kV. Yeah, I don't want to give the wrong answer, but I think that's it.
And one from Chris Forster, be useful to understand the annual operational hours of the water source heat pump as it's covering the base load.
Yeah, we had to get all that. So in terms of the marine license, we had to essentially the heat pumps are always going to be operating.
Yeah, basically
all through the year,
24/7. Yeah,
24/7. But it does fluctuate. I just had to send through some modelling data to the Environment Agency about a couple of months ago in terms of because we've got a permit for how much water we can take out and put back in, and I've got the figures for that. Can't remember exactly what it is now, but it does fluctuate. But essentially, it's operating all the time in theory.
Good. Well, that's all the questions, Gerard.
Yeah.
So on behalf of CIBSE, I'd just like to thank you very much for the presentation. Extremely informative. I guess if there's any more questions that do come through, we can just maybe forward them on to you to answer possibly in your own time.
Yeah, that's fine. No problem.
As I said, the slides will go up on the CIBSE Northeast website in the next week or two.
Yeah.
And that just leaves me to thank everybody for attending, and hope you found it as informative as I did. And thanks very much to Gerard.